All right, our next topic is second order kinetics. So let's take a look at that. All right, second order kinetics are by definition those for which the rate law is either rate equals K times the concentration of some reactant squared, right? Or rate equals K times the product of two different reactants A and B. And both of these are second order reactions. But in this section and also in your textbook, we're only going to deal with this type of second order reaction. The other type, the one on the right hand side, is second order, but these are mathematically really difficult to deal with. So we're not going to deal with these. Not here anyway. If you're interested, you'll be able to work on those types of kinetic reactions when you get to PChem. And they are kind of fun, but they're mathematically a bit more intense. All right, so second order reactions, what causes second order reactions? They're the ones for which the rate determining step in the mechanism involves two molecules colliding with one another. So anytime you have a bimolecular rate determining step, you're going to have second order kinetics. So here's an example of a reaction that's second order. Nitrogen dioxide reacts with carbon monoxide to make nitric oxide and CO2. And we've got some data over here, data table on the left, and then a curve showing the concentration of nitrogen dioxide. The graph doesn't say NO2, but that's what we're plotting in that graph over there. So the first thing you might notice is that, at least to a first approximation, the curve of concentration versus time looks a bit like a first order reaction. Second order reactions and first order reactions look kind of similar, except that the second order reaction has a slightly steeper curve to it, has maybe you might see a more sharply bent elbow down here. So whereas a first order reaction might look like that, be a little bit more gradual, the second order has a more abrupt change to it. But when you're just looking at them, you just take a glance, it's kind of hard to tell which is which. So here's another way that you can tell if something is second order, or at least you can tell if something is not first order. Remember that first order reactions have a constant half-life. Second order reactions do not. So if we look at the half-life for this reaction, we start with a concentration of 0.5 molar, right? So one half-life would be the time required to get to 0.25 molar. And so that is, looks like maybe about 75 or 80 seconds, right? Then we look at the next half-life. Next half-life would be the time to go from 0.25 to 0.125. And so we draw that out there. And you can see that takes us out to about 250. So that half-life is maybe about 170 seconds. And then the third half-life would be the time to go from 0.125 to 0.0625, something like that, right? And that would be, it's kind of hard to tell exactly, but somewhere in that ballpark. Now, if you look at the half-life, right, our first half-life was really short, about 70 seconds. The next one was maybe 170, 180 seconds. And then the next one was maybe about 300 seconds, something like that. A little over 200, maybe a little under 400 seconds. But the key is the half-life is changing. The half-life keeps getting longer. So if you don't see a constant half-life, it can't be first order. And if it has that same kind of shape and it's not first order, then it's second order. All right. All right. So a better way to look at these to really prove that something is second order, the constant half-life rule proves that it's not first order, but it doesn't actually prove that it's second order. A way to prove that it's second order is to do a linearization, just like we did for first order reactions. And so if we start, move over a little bit, start with this definition. For the second order rate law, you can use differential equations to get a equation to describe the concentration of the reactant as a function of time, and the reaction that you get involves reciprocals. We've got the reciprocal of the concentration at some time is equal to the reciprocal of the initial concentration plus kT. And this is a really pretty equation. That's a nice way to learn it. That's the way I would write it down. But I am going to do one other thing with this, and that is I'm going to switch those last two terms on the right hand side. And if we do that, we get reciprocal of the concentration at time t is equal to the reciprocal of the initial. No, we don't, because I just switched those. Sorry about that. Okay. Reciprocal of the concentration at time t is equal to kT plus now 1 over the original concentration. And the reason I'm writing it this way is because if we plot the reciprocal of the concentration as our y value, right, and time as our x value, then you can see that this equation is in y equals mx plus b format. And what that means is that the reaction, or the data, if we plot the reciprocal of the concentration as a function of time, we will get a straight line, and the slope is equal to the rate constant. And we don't use it as often, but the y-intercept is equal to the reciprocal of the initial concentration. So we can use that graph to get the initial concentration if we didn't have that value. All right. So the way we would use this, let me clear a little bit of space here. For each of the values in the table, for each of the concentrations, that is, we just calculate the reciprocal, right? Remember, reciprocal just means 1 over, right? So the reciprocal of 2 is 1/2, reciprocal of 4 is 1/4, so on and so forth. Right? And so if we calculate the reciprocal of the concentrations, we can make an extra column in our table here, reciprocal of the concentration, and the units on this are going to be reciprocal molarity, okay? And those units are important. So for the first one, concentration is 0.5 molar. You can just, in your calculator, 1 divided by 0.500, and that'll give you 2.00. You've also got a 1 over x key on your calculator, which looks like that. If you want to play around with learning all the different keys, you could type in 0.055 and then push your 1 over x key, and that'll give you as a result 2. However you want to calculate it, just take 1 over each of these values. For the second one, you should get 3.289, and then for the next one, 4.566, okay, and so on and so forth. And notice these values are all positive. When we calculated logarithms for first order reactions, we very often had negative values, but these are all going to be positive. All right. Let's see what this looks like when we get all of those values calculated. Right. So if we take all of those values and put them into our table, got this right here, and plot this to see if we get a straight line. And again, the slope of that line is equal to the rate constant, and the intercept here is 1 over the initial value. You can see that that fits with what we had in our table. Okay. All right, so let's use this to calculate the value of the rate constant, because the rate constant, of course, is a very useful number, right? We use that a lot. So let's calculate the rate constant for this reaction. So, as we said before, K is equal to the slope, right? And notice that the slope is positive in this case, so K is not negative slope as it was for first order reactions, but K is actually just the slope. Right? So for the slope, we just need to pick 2 values on the line, and I'm going to find 2 that are kind of close to grid lines. That'll make it a little bit easier. So here's one right here, and let's see, how about this one where it crosses here? All right. So this gives me a line, and that's our change in the y value, and that is our change in the x value. So our slope then is the second y value, which is about 12.2, right? And the units here, remember the units on that y-axis are reciprocal polarity. Okay? And then I'll subtract from that the y value for that first point, and that one's right on the line. I chose it so that it was on the line. That's 6.0 reciprocal molarity. And then take the x values. The second x value is right at 400. And the first x value is right between 100 and 200. So we'll call that 150 seconds. All right. And if we subtract those in the numerator, we get 6.2 reciprocal molar. And on the bottom, we get 250 seconds. When we put that in our calculator, I got 0.0248, 8. And then we'll look at the units. We have, in the numerator, we have reciprocal molarity, and in the denominator, we have seconds. So that's also in the denominator of our result. And remember, this is really important when you're calculating rate constants, because the units of the rate constant change depending on whether it's first order, second order, or 0th order. So it's always important to include those units. Also, you need the units in there when you do subsequent calculations to make sure that everything works out properly. So K then is 0.0248 reciprocal molarity seconds. All right. Now, since we, if we did this on the chalkboard in class, we'd be making pretty broad estimates trying to figure out what these points are. Since we've got a graph here, we probably have pretty good points. That should be a good estimate. But we can, if we have a data table, we can get an even better measurement of the rate constant. So let's try that. Okay. So when you're calculating the slope of a line, you're really just looking at the change in an x-coordinate and the change in a y-coordinate. And you can estimate those values from a graph, or if you want, you can, if you have a table available, right, then you can just choose values from the table. And I'm going to choose these two. All right, I'm just going to choose 100 seconds and 500 seconds. And so K then is just going to be the change in that y-coordinate, or y value if you want to say in this case, divided by the change in the x-coordinate. And y's are the reciprocal concentration, and x is time. Right? So just take our second value here. The second one, we got the y value 14.925 reciprocal molar minus the y from the first point, which is 4.566 reciprocal molar. Divide that by the x-coordinate for the first point, which is 500 seconds, minus x-coordinate for the first point. I think I might have said first point both times. It's the second one minus the first one. And we'll just subtract each of these. In the numerator, we get 10.359 reciprocal molar, and in the denominator, you get 400 seconds. And put that in your calculator, you get 0.0259 reciprocal molarity seconds. And you can see that's really close to what we got when we estimated it from the graph. That's good. I'm also going to say the same thing that I say all the time, which is the rate constant is called a rate constant because guess what? It's constant. So you ought to get the same value regardless of which pair you choose, right? So you could choose 50 and 200, right? Or you could choose 0 and 500, right? You choose any pair you want and you ought to get the same result. So I would encourage you, definitely, if you've got an exam and you're calculating a value and it's important that that value is correct, I would definitely recommend calculating it more than once to make sure you're getting the same result. If you don't get the same result, you're making a mistake somewhere. Maybe you thought it was second order, but it was actually first order or something like that. But try calculating that from a couple of different pairs of data and make sure you get the same result. All right, now let's see how we can use this K now that we've got the rate constant. So the types of questions that we might be asked for second order reactions are the same kind of things you had for first order reactions, right? Based on the data that you've got, and in this case now also the rate constant. Hold on a second. 248.259. Let me double check my rate constant. I've got two different numbers written down. Let me double check my math. Hold on a second. Okay, sorry about that. This number is correct. I had 0.0249 in one place and 0.0259 in another place in my notes. It looks like in one case I just wrote it down incorrectly. All right, so this is our rate constant. We might be asked a question like, what is the concentration of nitrogen dioxide at 300 seconds, right? And the first thing we ought to do, as always, is look at the data table and see that 300 seconds falls right in there. So the concentration ought to be somewhere between 0.14 and 0.067, right? So don't really know what it's going to be, right? But at 300 seconds, it's maybe going to be around 0.1, maybe 0.11. I don't know, something like that, right? Probably not as high as 0.12 or as low as 0.08. Okay, but somewhere in that ballpark. And by definition, obviously somewhere between 0.14 and 0.067. If it's higher than 0.14 or lower than 0.067, there's absolutely a mistake somewhere. So you need to go back and find the mistake and fix it. So, all right, let's go ahead and try this and see if we get a result that makes sense somewhere between those two. Let's start with our equation. Okay. And so 1 over the initial concentration is 1 over 0.500 molar plus our rate constant, 0.0259 per molarity seconds times 300 seconds. All right, and so for the first one, 1 over 0.5 is 2. So that's 2.00 reciprocal molar, plus on the right-hand side here, when we multiply the rate constant times 300 seconds, we get 7.77. And notice you've got, if for units, reciprocal molarity and reciprocal seconds times seconds. So when you've got those, the seconds here cancel with the seconds there, and you're left with reciprocal molar. And of course that has to be the case because you're adding this number and that number. And if you add two numbers together, they got to have the same units, right? Else you can't add them. So 1 over the concentration of NO2 is 9.77 reciprocal molar. And so to solve that, we just take the reciprocal of both sides. Right. And so on the left-hand side, basically we're just flipping the fractions, right? So on the left-hand side, if we take the reciprocal of 1 over the concentration of NO2, then we just get concentration of NO2. And on the right-hand side, reciprocal of 9.77 reciprocal molar, that's just 1 over 9.77 molar. And to solve that, just put it in your calculator. 1 divided by 9.77, or you can use that reciprocal key if you want. And when you do that, you should get 0.102. And notice that the unit's molarity is in the denominator of the denominator. So that comes back up into the numerator, as it should, since we're trying to calculate a concentration. All right. And notice also that that agrees pretty well with our initial guess based on the data table. So that looks like a good calculation. All right. All right. Now, since you've got this data table, you can try to make some more problems on your own, right? You might decide to calculate the concentration at 150, right? And at 150 seconds, you're going to be right in there, somewhere between 0.219 and 0.14. So, I don't know, 0.18, something like that. That seems like a reasonable guess. You might try that calculation, see if you get 0.18 or something close to it. What you can also do, really, if you want, you can pick an actual value from the table. Right? You can say, what is the concentration at 50 seconds? Plug it in, run through the math, and see if you get 0.0304. Right? So you've got a whole bunch of practice problems that you can do on your own based just on this one data set. So I would encourage you to go through and try a couple of those and see how they come out, and hopefully they'll work out great and you'll be really happy with yourself. That's the goal, right? That's the goal of everything we do, right? Get good answers and feel good about yourself. All right, some of the things we're going to be looking at in this video are physical states and phase changes. Of course, we can work how those the other way, where you're given displayed in a phase diagram, and you have to solve for the phase diagram. We're also going to be looking at so in this case, it's asking at what time is the concentration equal to including the triple point, molar, critical point, critical temperature, that's going to be right here, normal boiling and melting points. Right. We're going to look 100 seconds, in particular at the phase diagram of water, just a little bit after and that. Also phase diagram of CO2. 120 seconds, 130 seconds, and like something I didn't put on this list, but I think is important, is we're going to get a little bit of practice. 72 seconds, right? Reading, not 420 seconds. Right? Maybe it'll be 120, maybe it'll be 150, maybe it'll be 110, you know. Interpreting, but it should be pretty close to that. Phase diagrams. All right, and that's important. As always, let's start. It's important because that's sort of the whole point here. But also be aware that on quizzes and exams, I'm just going to use it's likely that you'll have a phase diagram, and you'll be asked to interpret it and answer questions about it. A is our generic symbol for a reactant, so we can do that. All right. Now, since we want to solve for T, let's try to get T by itself. So we can subtract the initial concentration from both sides, or the reciprocal of the initial concentration. So if we subtract 1 over A0 from both sides, we get negative 1 over A0 on the left, and then we remove it from the right. And now we could divide both sides by K, but I feel like that would just get kind of messy. So I'm going to leave KT on the right-hand side for now. And so if you want to move it over and do your algebra that way, you're certainly welcome to. Okay, so just put in our concentrations, the initial concentration and our target concentration of 0.2 molar. We put these in calculator, and 1 over 0.2 is 5 reciprocal molar, and 1 over 0.5 is 2 reciprocal molar. That equals KT. And I'm going to go ahead and clear a little bit of space. All right. So on the left, you got 0.5 reciprocal molar minus 2 reciprocal molar. That's just going to be 3. That's KT. All right. And now let's solve for T by dividing both sides by k. All right. All right. We'll divide by k. I'll go ahead and put in the value for k. K is 0.0259 molar second time. And if we look at our units, we've got reciprocal molar in the numerator and reciprocal molar in the denominator, so those cancel. We're left with seconds in the denominator of the denominator, so that's going to come up to the numerator, just as we would expected since we're calculating a time. And put that in your calculator, and I got 115.8, right? And that's good. That's right about what we estimated by looking at the data table. So if we're rounding to 3 sig figs, we'd report that as 116 seconds. And again, you can make up a couple of your own questions, right? So at what point will the concentration be 400, right? Should be somewhere in here, maybe around 10 or 15 seconds, you know. At what concentration will it go to 0.05, right? That's off of the table, but it should be a little bit over 500. And again, you can put in values that are directly in the table, try to calculate the time at which the concentration will hit 0.14 and see if you get 200 seconds. All right, I bet you will. I bet you'll get 200 seconds. All right, so give those a try, and we will pull this together. So the things we said in this video reviewing second order kinetics is that second order kinetics are reactions that obey this rate law. There's actually another rate law as well, different kinds of reactions. Those are also second order, but those are not covered by the equations described in this section, and they're not in your book, and we won't do them in the course. Right? Second order reactions, if you plot the concentration as a function of time, they look a lot like first order reactions, except the curve is a little bit steeper. And if you look at the half-life, you'll see that the second order reactions do not have a constant half-life. Okay, that's a really important clue. All right. For second order reactions, you can make a linear graph if you take the reciprocal of the concentration and plot that as a function of time. And when you do, you'll get a straight line with a positive slope, and the slope is equal to the rate constant. The y-intercept is also equal to the reciprocal of the initial concentration, although that doesn't come up as frequently, because usually we have that number. All right. And finally, the concentration as a function of time is given by this equation here, and this is fine. I guess this is the way it printed out using PowerPoint, but it might look nicer to you. It looks nicer to me, at least, like this. Okay. So that's an important equation that you should know. All right, fantastic. Thank you, everyone, for hanging with me through second order kinetics. And the next thing we'll do is zero order kinetics. So I will look forward to seeing you then.